And I'm also happy to still see so many people here, even after all the main lecturers finished their things and went home, at least Mature did. I was hoping that I could just point you in the direction of Mature if you had questions, but he fled, so I guess I'm going to have to try to answer any eventual questions. Okay, so what I'm going to tell you about today, classical density functional theory. It's basically the same thing as what Mature has been telling you about all week, except there's no kinetic energy. Everything is classical. So back when we, it's a project that I did with Mature and Michal Jeks, who was in Prague, when I was a postdoc with Mature in Paris. And when we started the project, there was, I mean, the amount of results on classical, on density functional theory is very scarce. So back when we started, there were really only 2 papers justifying the local density approximation. One for the classical 3D Coulomb gas, which is non-quantitative, it's just a qualitative limit statement, and then there's the quantum 3D Coulomb gas that Mature told you about. There is a quantitative bounds. We wanted to try to extend this to a more general set of interaction potentials. And we thought, yeah, we'll just start with the classical case because we can be a little bit more rough around the edges and it seems easier. And then it ended up taking us 3 years anyway. Okay. So, a little bit of an outline of what I will talk about. First, I will introduce a setting, just tell you which functions we work with. And then I will talk about representability and bounds, I mean, which densities can be represented by an any-body state with density, this exact density and with finite energy. And we ask if we can derive some bounds on the energies only in terms of the density, like local bounds. Then I will talk a little bit about thermodynamic limits because I need this to state our main results, which is the local justification of the local density approximation in the grand canonical setting again. And maybe if there's time, I will talk a little bit about how to, or give you a vague idea about how to attack this. Okay. So, we consider a system of identical classical particles. They interact through a pair potential W, and then in the canonical picture, when you have a fixed number of particles, the classical state is a symmetrical probability distribution on your space, the n-fold product of your space, and then the free energy in this state is just the interaction energy and then some entropy. Okay. Everything I'm going to tell you today also works at 0 temperature, but just for the sake of simplicity, you can think of the temperature being positive. So we really have this entropy term, which is helpful in the sense that it forces your densities to be regular. I mean, absolutely continuous with respect to the Beck measure on your n-body space. Okay. So then if we fix the density with mass n, then we ask, well, what is the minimum value of this? Okay. So that is the classical counterpart of the canonical density function. Of course, we also have the grand canonical guys. I will talk a little bit about both, because we can prove more in the grand canonical setting than we can in the canonical setting. Grand canonically, the state is just now a family of measures where each Pn lives on your n-body sector, and they normalize such that the mass is 1, actually, when you sum over all the sectors. So you can think of a grand canonical state as a convex combination of canonical n-body states. And then, of course, we have the similar definition for the grand canonical minimal free energy. And just to be clear, the density of this grand canonical state is just the sum of the n-body densities, or the sum of the densities for the n-body guys, which is just the marginals multiplied by n, and so on. So then, of course, you can put this into the context of, Gibbs energy. If you, like Mathieu mentioned, you can do a two-step minimization. If you have the usual free energy with an external potential V, I think you should also think of a chemical potential being hidden somewhere in this guy V. So that's just the infinite all grand canonical states, but we can split this up into a two-step minimization where we first minimize overall states with a fixed rho, and then minimize over rho. And then you can see the external potential just splits off into an integral V against rho, so we can disregard any external potential contribution when we just look at these guys. Okay. So also here you have a formulation of the problem in terms of inverse potentials. I mean, given rho, can we find a potential V such that the corresponding Gibbs state has density rho? Okay, so this terrible expression is just the one-body density of a Gibbs state in the grand canonical picture. If we can find a potential such that this holds, then we have this equation between the energy at fixed rho and the usual guy, which, by the way, we all should know this. This is minimized by Gibbs state, and we all know that the minimum energy is minus T log partition function. I will not talk a lot about the inverse problem, if at all. I will just mention there are some results about existence of this inverse potential V in the grand canonical, also canonical cases. It's a little bit some old results really, but the problem here is that calculating the inverse potential is still super difficult, and you don't really. I mean, we know a large class of interactions where this guy exists, but we cannot say much about what the potential actually is. So in many cases, it's a lot more feasible to just attack this problem from the point of view of a variation of problem like this. Okay. Yes? Because there's no kinetic energy. There's no kinetic energy. Okay, so in classical statistical mechanics, of course, you have kinetic energy in your system, okay? But the phase space is just momentum variables and position variables. And when you minimize over the energy prescribed by some Hamiltonian, the kinetic energy always separates, so you can minimize the two things separately. So, in that way, the question about kinetic energy in the classical case becomes very easy all the time. So we just, for simplicity, we just exclude it. there is one case, the 1D hardcore case, where the inverse potential is known explicitly. So you have explicit formulas for this guy. I will not talk about the hardcore case. Not that much is known. It's a very difficult problem. I just want to mention that this result exists and it's very nice. And recently, Dinh Thi NGUYEN calculated the inverse potential for uniform small densities as a convergent power series. Okay. So this result you can probably also massage a little bit to get a local density approximation, but exclusively for densities that are uniform. Okay. So natural questions about these two guys, GT and FT. Is it even clear that given a density, let's just say an L1 function, well, when are these guys finite? So this is the question, which densities arise as a one-body density of some many-body state with finite energy? The answer to these questions depends on which interaction potential we have, which I have not told you about yet. I will in a minute. Local bounds. How can we bound these in terms of rho? And I mean the difficulty for these kinds of questions is really construction of trial states that have exactly a given one-body density. Normally you say that upper bounds on these kind of things is hard, you just build a trial state. But when you fix the density, then it's actually a little bit more difficult. So the first part of this talk, you can view it as a crash course in how to build such trial states. And then in practice, how can we approximate these guys? And that is where I will say local density approximation. And that comes in at the end of the talk. So, a few initial remarks or observations. Any canonical state is also a grand canonical state. So you have this bound always when rho has integer mass. When rho doesn't have integer mass, when it has mass n plus some small thing t, then you can still write rho as a convex combination of a guy with mass n and a guy with mass n plus 1, and then just use concavity of the entropy to arrive at a bound like this. So in this sense, the grand canonical energy is always bounded from above by the canonical energy. So you can say, I mean, if we can bound this guy, then we also have the bound for this guy. In practice, it's a lot easier to derive bounds with the grand canonical guy, usually. There is one exception where bounding this guy is easy. It's in the case of weak interactions, meaning if you have an interaction potential that's everywhere integrable, then you can just take an uncorrelated state. Then calculating this guy, you just get the interaction energy plus the density of rho, and when W is integrable, you can just use Young's inequality and you get something like this. So this is a local bound. Of course, it only works when W is integrable. Okay, so this case, where you have an integrable interaction that's already solved, it's very easy. So I will not talk about that anymore. Okay, so a bit about the interaction potentials that we can handle. We want W to be a lower semi-continuous and even function, which is classically stable, meaning this sum is bounded from below by some kappa times n, no matter which configuration of particles you have. We also want it to be upper and lower regular, which means it's bounded from above and below by this kind of function in near the origin, it grows like x to some power alpha, and at infinity it decays like x to some power s. So we take any alpha between 0 and infinity, and any s that's bigger than d, such that the tail is integrable. Okay. You might remark here that when talking about universal upper bounds for the energies, we don't need the lower regularity of W. This is really mostly important when I start talking about the local density approximation. Okay. So for the most part, we will just assume that this alpha is bigger than D, because otherwise this guy is integrable. And then we already did everything. So the problem that you run into here when alpha is bigger than D is that your particles really don't want to be too close together. So when you construct trial states, you really need them to have some correlation between the particles. They want to stay a little bit far apart. I mean, how far depends on the interaction. So another easy observation, given stability of W, is that the energy is bounded from below. As soon as the density has finite entropy, then you can just plug this bound into the expression for the energy in any state, and then you're left with maximizing the entropy fixed density. This problem is pretty easy to solve. It's attained by the Poisson state, which is a grand canonical version of an uncorrelated state, and the entropy here in this state is just the entropy of rho plus T times integral or minus. So lower bounds on our energy function is very easy when you have stability, which I guess you want to have. So what can we say about upper bounds? And I want to start easy. Dimension 1. So in the canonical case, we can actually prove a very nice bound for any density with integer mass and finite entropy. The minimal free energy is bounded by integral rho squared, something with rho, something with entropy, and then we have something that depends on alpha. So the reason this term, I mean, always the case where alpha is equal to the dimension is special because because this guy is not integral at infinity. So you have logarithms popping up everywhere. Okay. So I say, how do you prove this? You draw a one-dimensional chessboard, and maybe it's not completely clear what I mean by this. So I mean, we can do this in detail. It's very instructive for about how we do things in general in higher dimensions also, and it's not too painful to go through it. So what you do? Say you have some density, okay, and then you split the real line into intervals. They don't all have the same length, okay, and then you color half of them white and half of them black. So this is your one-dimensional chessboard. So just for the sake of simplicity, okay, we take alpha strictly bigger than 1. So we don't want to talk about these logarithms popping up, and we take s equal to infinity. Just W is 0 outside of a small ball. So we only have the interaction of the origin, the core of W. Okay. So what I just told you, we split R into intervals. We take two families, black and white intervals, we call them LJ and LJ tilde. Okay. And what do we want these intervals to satisfy? If you integrate rho over any of these guys, we want to get exactly 1/2. We can do this, it's very easy. We just start from minus infinity, integrate until we reach minus 1/2, and do this again. This gives us 2 n intervals. So we get 2 families of n intervals each. Okay? And then what you do is you write rho as a convex combination of 2 guys. This is 2 rho characteristic functions of 1 family of intervals plus some 2 rho characteristic function of the other. Okay. That's very easy. So what we want to take as trial states. Of course, it's just, we want to take a trial state for each of these 2 densities. We just take the symmetric tensor product. Like this. So our final trial state that has density rho, we just take the convex combination of Q and Q tilde. Okay. And now what remains is just calculating the energy in this state. So I will just do it for one of them because the argument is completely the same. So the first thing, the entropy of Q. So by definition, this is Q of x log Q of x dx. Okay, so if you plug in that this is the anti-symmetric tensor product, I think I forgot a, supposed to be an n factorial. N factorial of x. Okay. So you just by definition what you get is really 1 over n factorial, then you sum over the symmetric group tensor to rho indicator function L sigma j. And then you get log, you do the same thing in here, you see it as an n factorial killing an n factorial, and then you get sum over these guys, but all our intervals are disjoint, so only one of them survives. So this is this guy. Okay, you see this guy splits up into a sum, and you just mess around a bit. This gives you sum integral 2 rho indicator 1, okay, 2 rho indicator j. So which is just the integral over the union of the LJ's 2 rho or 2 rho. Okay. You have the same bound for the other guy, just with the other set of intervals, and then you use concavity of the entropy to bound the entropy. This guy by the sum of the entropies of these guys, which have the this form, which is what we were looking for. Okay. The interaction energy is a little bit more messy, not that much. So, what is that? That's the sum I less than j of n wx I minus x j with respect to q. So if we use our assumption on w, we can estimate this by integral 1 over x minus y to the power alpha, and then we get the two-body density. Okay. You can calculate what that is. It's not that difficult from definition. I won't do it, I will just tell you what you get. Get 1 minus 1 over x minus y to the alpha, and then you get 2-row indicator L I x, 2-row indicator function j y dx dy. Okay. So now you just say x is in Ly, y is in Lj. We just bound this this distance from below by Ly, so this is Lj. When x is in here and y is in here, this is smaller than just the distance between the intervals. So what you get when you do that, you just get 1 from the integral here and 1 from the integral there. So we have the sum I less than j. There's a kappa, 1 over distance between the intervals. Okay. So we need some smart way to estimate that sort of thing. So this is where we start looking at the neighbors of the intervals. So for each I, the interval Li, we look at the two neighbors that are intervals like from the other family, and then we just pick the smallest value for these intervals. Li is dt to 0. And then you get the good idea to reorder your intervals such that these lengths, minimal lengths of neighboring intervals is increasing. Okay. And then you fix I. If you take a j that's bigger than I, by definition, then the distance between Li and Lj is bounded by first a to j, which is bigger than a to I, by the way we order things. And then you pick some points, xj and yj, such that this distance is exactly the distance between xj and yj. If we go over here, then this is xj and this is yj. Remember that we fixed the interval Li, and then we consider all the other intervals such that a eta j is bigger than eta I. Okay. Then what you want to do is you want to take the neighboring interval of Lj that points in the direction of Li. So this guy here. It's Lk tilde for some k. I don't know which k. But then what you do is you just go a little bit into this interval. Call this Lj star. How far do we go in? Eta I halves. Halves intersect. Okay. So this interval now, which is an extension of Lj, it has length eta I halves. And then this can be bounded by above by the distance between xj and y, distance between xj and yj, for all y, etc. Okay, so that's just saying a bit about the distance between points in here and then xj. So now, we wanted to bound these guys, right? So if you sum from I plus 1 to n, 1 over distance Li to j, to the alpha. Okay, so we chose xj and yj such that this is exactly equal to this distance. So we get another bound if we replace by this distance. That happens for every y in here, so if we take the average, we get another bound. N into j star 1 over xj minus y to the alpha y. You just calculate. And then what you realize is that no matter which j we have here, the distance to the origin is bigger than eta halves. So this is smaller than some constant times integral eta halves infinity 1 over y to the power 1. And there's still an eta here. When you calculate this, you get some constant eta I to the alpha. Okay, so this, we have essentially replaced n terms by one term. And now we're happy because if we sum over the additional terms 1 over eta I to alpha, what we get, the eta i's was something like the minimal length of the neighboring intervals. So it's some sum. We don't get all the neighboring intervals. Maybe we don't get the end intervals that are infinitely long, but you get a sum, something like this. And then I say, by definition of our intervals, you can use Hilbert inequality to bound this guy. So you get some constant integral over Lj tilde rho to 1 plus alpha. this is exactly what we want to see. So the entire point here is really just to write the support of your density as a union of compact sets where the density has a fixed mass inside these compact sets. And that is the entire point of the approach. Okay. Then immediately you can say, I mean, you can do the same thing in arbitrary dimension, just cutting ID into slices instead of intervals. I mean, by the same construction, you get the interaction energy is bounded by a sum like this. This is certainly finite. So we immediately have that any density is representable. It's an easy corollary. So the question of representability is pretty easy in the positive temperature case. For instance, if you take a hardcore potential, then it's not so easy. It's a very difficult open problem, classifying the set of densities that are represented.
Okay. What happens to the alpha when you have to go to the 1 plus alpha and now you say low is 1 is enough?
So I'm just saying, in one dimension, we have this bound in terms of integrals of rho. In arbitrary dimension, we can do the same construction, the same trial states, but we don't have, in this case, a bound on these distances. Because in this case, you cannot use Hölder's inequality to relate the length or the breadth of the slices to the integral of rho 1 plus r.
No, but just ask, even in one dimension, right? So your bound seems to suggest you want rho and carry 1 plus alpha. Now you say rho and 1 is enough.
Yeah, I'm just saying, no matter what rho, which rho we take, we get to this guy. This is finite. If rho is not, rho to 1 plus alpha is not integrable, then I have no way of controlling how big this is. So I just don't get a local bound in terms of rho. I can say it's finite, but I cannot say any more than that. Okay. So what do we do in higher dimension to get bounds like this? The idea is sort of the same. So what we can do for the grand canonical bounds is this. I mean, the bound is exactly the same. Instead of 1 plus alpha, you have 1 plus alpha over d. And how do we do this? I mean, you first say if your density has mass less than 1, then you just take a state that has either 0 or 1 particles. And there's no interaction energy, and the entropy is just bounded by the entropy of rho. You're done. Okay. If you have more mass, then we can fix some constant, and then around each point in the support of rho, we take the largest cube around this point, such that rho has mass c inside this cube. Okay, so it's a little bit like the intervals that we had before. It's just, I don't tell you what this c is. Okay. So this gives us a cover of the support of rho. If we assume that the support is compact, we can reduce it to a finite cover, but then there would be some overlap. Turns out we can control this using the Sigurich cover layer, which you can read about in a book by de Guzman, or in a newer book by Frank Laptop in Weidel, which is where we learned about it. And it states that when you have a cover like this, where you attach a cube to each point in your compact set, you can extract a set of points, so some families of points, say x, j, k, where k is between 1 and some universal constant, and j is just whatever, depending on k. Such that the corresponding cubes, there are finitely many of them, they cover the support, and the overlap is no more than 2 to the d. It's very important that this is a universal constant. And then on top of that, you can choose them such that in each family for fixed k, the corresponding cubes disjoint. Even more, we can choose them so that there is a minimal distance between the cubes in terms of the side lengths of the cubes. Okay, and then, I mean, what do? You do this before. You have this this function that counts the overlap of our cover. This function by the lemma is bounded by 2 to the d, and it's bigger than 1 on the support. So then we can write a partition of unity by just summing over these guys and dividing by 8. Okay. Multiplying this by rho, we get rho as a convex combination of these guys. So it's a convex combination over some guys that live in each family of cubes, and in each cube, the mass of these guys is bounded by 1, because this is where I tell you how we choose C. It has to be small enough so that it cancels out this universal constant. Okay, so I just told you how to build trial states when the mass is smaller than 1. So we just do that again. For each box in a fixed collection, we just put this guy, and then we take the product state of all the cubes in the collection. That gives us the trial state pk for each fixed k, and then we just take the convex combination of these guys. And this is the trial state we use in the grand canonical case. And then you do the same thing as just did in the one-dimensional case. And here you get a bound on the side lengths of the cubes in terms of integral of rho to 1 plus alpha over d, just by using Kepler's inequality. But it's really important that your cover is consists of compact sets, or at least bounded sets, so that you can actually do this trick. So it's just, this works very well in the grand canonical case, but not so well in the canonical case, because you cannot really control the mass that we have in each of these collection of cubes. Okay. But what can we do in the canonical case? Same kind of bound. There is one key difference here. There's an extra term popping up, which we're very not happy about, because it's a non-local term. So what is that? This function r is defined like the side lengths of the cubes before. It's just the largest radius such that the mass rho in ball around x of this radius is equal to 1. It sort of tells you, or gives you an idea how much space you need to put a particle in x when you build trial states. So yeah, we're able to prove a bound that's almost like the one we have in the grand canonical case, but we just have this extra term popping up. So why is that? Just let me gather some easy things about this function r. It's always positive, and when x goes to infinity, it behaves like the length of x. There's a connection to the Hardy-Littlewood maximum function. If you take 1 over the volume of a ball of length r of x, by definition this is the same as the average of rho over this ball. So if you just take the supremum over all radii, you get something bigger, and this is the definition of the Hardy-Littlewood maximum function. So we have a pointwise bound between this r and the Hardy-Littlewood maximum function. This is useful because we have the Hardy-Littlewood maximum inequality that relates the p norm of the maximum function to the p norm of rho, as soon as p is strictly bigger than 1. Okay. But this doesn't tell you anything about how we build a canonical trial state. And it turns out we pull it out of a hat. It comes from an optimal transport result. So Mathieu mentioned a couple of times that the density function theory at zero temperature is really a multi-marginal optimal transport problem. So there's an abstract result by Colombo-Guimond-Strah that says that given any density with integral n, there is an n-particle state with this density such that if you are in the support of your state, the distance between the particles is bounded from below by this stuff in terms of the function r. Okay, so this guy is useful to say a little bit about the hardcore case. We just need this bound. So this really says that if you take a configuration of points in the support of your state to transport, then if around each point you put the corresponding ball of radius r of x divided by, say, 6, then your balls are disjoint. Okay, so this is useful. Maybe I should remark that, this guy shows up from an abstract result. We don't really know what it looks like, except that it's almost definitely singular with respect to the Lebesgue measure. So to use it for the positive temperature case, you need to do some sort of a regularization. I won't talk too much about this, but just mention that just using this characterization of the support is enough to give a good bound on the interaction energy along the same line of argumentation that we did before. So you just estimate these guys by some average over balls. And then you get a bound in terms of this R function. When you plug that into the interaction energy, you end up having to estimate something like this. And then just using Hölder's inequality in conjunction with the Heidelberg maximal inequality, you get something like this. Okay. So it's very good for the zero temperature case. We don't know what the state looks like, just that it exists. So it's a little bit spiritually unfulfilling because we cannot say how we should construct these things. For the positive temperature case, you can do a regularization. It's called the block approximation, where you locally replace the state with a pure tensor. And it regularizes the state while keeping the density fixed. And this is why we are able to get a bound for the positive temperature case too. But we have an error from the entropy that we don't know how to control. Okay. Still, this bound is good for some applications. Okay. So now, for the rest of the talk, I will tell you a little bit about the local density approximation and what we can actually prove for this. So just to remind you what we're looking for. We're going to the grand canonical case now because that's the only case where we can actually prove anything. We want to, for any rho, estimate the minimal free energy in terms of some local function. And in this business, what we wanted to do was to generalize previous results of Mathieu, Robert, and Elliot Lieb to a case, the case of short-range potentials, because the only results along these lines that existed at this point, it was 3D and Coulomb. And it was it all relied heavily on Graf-Schenker inequality, which I will not tell you about. It's just it's a tool that you can use to control a screening tool for the Coulomb potential in 3D exclusively. Okay, so there's not a lot of results that you can cite in terms of, I mean, in the context of providing quantitative bounds for this sort of approximation. So I need to tell you what this function f will be. It's the free energy per unit volume of an infinite homogeneous system at density. So a little bit of, we recall from statistical mechanics that if you don't fix the density, just take the minimal canonical free energy in some set under n, and then you scale up the domains lambda n suitably. The limit exists, and it's this guy. This is focal at this point. You know the function is convex and C1. Okay, so it turns out that when you fix the density,